So we've discussed two different ways to visualize the theoretical effects of main effects and interactions with a 2x2 ANOVA. And again, when we're running a 2x2 ANOVA in SPSS, we're checking multiple significances. We're checking the significance of the difference in factor A. Is there a significant main effect of A? We're checking the significance of factor B. Is there a significant effect of factor B? And finally, we're checking the significance of the interaction. Once we've accounted for the variance of A and B, independent variable IV1 and 2, is there remaining variance that is left over that is explained by the unique combination in those various categories. So example, male CBT versus female CBT versus male psychodynamic versus female psychodynamic. So if we do find an interaction, we're not done. So again, we have additional layers of the onion to go down, and now we need to ask, where are those differences? What particular trend differences are significant? So again, from our theoretical viewpoint, we already determined that the difference between males going from CBT to psychodynamic theory was a +3 increase in means. But is that mean increase significant? We know that females going from a 20 from CBT to psychodynamic therapy went down 9 points. Now again, we know there's a significant interaction, so we can kind of guess that the largest difference probably is significant, and that is one of our larger differences, a reduction of 9 points in mean. Also, looking at the difference between males and females in cognitive behavioral therapy, we find again a 9-point difference. So again, in this particular case, we would know without even checking that that probably is significant as well. But our question is whether those 3-point differences are significant. So what we're going to be doing in this case is we'll still, even though we have a pretty good idea of what's going on, we're going to test all of those trend differences. So in a 2x2 design, we're going to test 4 mean differences, the actual individual means of each one of those combinations. So we're going to check to see, is the difference between males and females just within cognitive behavioral therapy significant? Is the difference between males and females just in psychodynamic theory significant? Is the difference between CBT and psychodynamic theory within males significant? And is the difference between CBT and psychodynamic theory in females significant? These 4 tests will give us a clearer picture to how these trends vary and when those effects are significant. And again, because we have the omnibus test of the interaction, we're somewhat free to just go in and find out where those differences are with these post hoc tests. So a simple main effects test is a form of post hoc test, but it is not a post hoc test itself. When we use the term post hoc test, we're usually referring to looking for differences within one factor. If we're looking for the differences between various conditions of multiple factors, we're going to use the term simple main effects test. So also make sure that you get it really solidly placed in your brain that a main effect is the difference between the means within one condition. A simple main effects is a series of tests looking for the nature of an interaction. Once again, I will comically note that the people that designed these tests were pretty mean in how they actually labeled things and named things. The names often are somewhat counterintuitive, but it is important to learn them and it is important to use those terms correctly. So again, we're just looking at our visual representation again from our example from the previous audio lecture, and we're just going to test each one of these differences. Is the difference between males and females in cognitive behavioral therapy, is that significant? Is the difference between males and females in psychodynamic theory different? Is the difference between CBT and psychodynamic therapy for males different? And is the difference between CBT therapy and psychodynamic theory for females different? And if we actually ran this data, what we would actually find is there really is only one significant effect that we're really looking at, and that is that across the board, there really isn't a significant difference between males and females if they're getting psychodynamic theory. There really is no significant difference in the increase or the effects of CBT versus psychodynamic theory with males. However, there is a large effect in the difference in the effectiveness of CBT versus psychodynamic theory with females. So if we were looking at the combination of these data, since there is not a significant difference between males and females in psychodynamic theory, there is not a significant increase in the effects of treatment for males between cognitive behavioral therapy and psychodynamic theory, and finally, there is a significant improvement with women or females with cognitive behavioral therapy. This data would actually say that if we had to choose one therapy or the other, we couldn't use both. We probably would just want to use CBT. There isn't a significant decrease for male performance. There's a significant increase for female performance, and therefore that's the one that we would choose. we don't actually have enough significant data to actually even make an argument that we should use psychodynamic theories for men and CBT for women, because there wasn't a significant difference in how men performed in psychodynamic theory versus cognitive behavioral therapy. So how we actually do this for SPSS, and you're going to definitely be going through this process in lab, but one of the things to recognize is that SPSS, for the most part, is a user-friendly kind of point-and-click statistical package. In other words, you're not having to do any real programming when you use SPSS 99% of the time. In other words, most of the techniques that we use in psychology is actually pre-programmed in to the actual program, SPSS. It's one of the reasons that I'm a fan of SPSS, is it definitely has its detractors, but it's probably the most user-friendly program. And even if an organization is not necessarily currently using SPSS, many times if you ask for that as a part of your package, if you're going to be doing analysis, it's something that most companies are willing to do. So it's not a bad program to learn, and also it's a very user-friendly program to learn on. There are other programs out there that are often being used, and there's a lot of them. One of the ones that's probably used the most is R, because corporations and companies love R because it's effectively a free user exchange program. The problem with R, though, is that it requires a lot of programming. And if you don't know how to program, if you're just cutting and pasting programming you're finding on Google, for instance, or Google searches, there can be some pretty big issues with that if you're really wanting to trust your data. Having said all of that, to run simple main effects in SPSS, currently we actually have to go into behind the curtains and do a little programming. So we actually have to go into syntax mode, and we have to enter a very simple set of code programming. And I've got it written here, and you can definitely cut and paste this out or simply write it through. But the things in color aren't going to change. You're always going to use these. So univariate, by, e-means, tables, and compare are always the same. What we're changing is the black print. The black print is your variables. So basically, we're telling it that we have two variables. We have intent of politics by gender, level, and education, and then we also have gender. So we have education level, we have gender, and our outcome is interest in politics. So what we have here is a univariate interest in politics, our DV, by gender, our first IV, space, by education level, our second IV. In the second line, we're adding gender times education level, the interaction, and we're telling it to compare gender, our first IV. This is going to give us both the statistically significant differences in our groups. It's also going to give us the means that we need to talk about this level. So again, this is an area where we're actually going to be doing a very small amount of programming to get SPSS to do what we need it to do. It's going to give us a table much like this. So in this one, we're actually comparing our dependent variable is interest in politics. Education level is our independent variable with 3 levels, school, college, or university. And we've asked it to look at school differences with gender, college differences with gender, and university differences with gender, and whether they're significant. And again, we find that there isn't a significant difference in school, there's not a significant difference in college, there is a significant difference in university. That's where our test is, and that's what we're looking at. So again, bringing this all together, I just wanted to kind of touch on how we conduct simple main effect tests in SPSS. You'll be spending more time on that in lab. So with an ANOVA, if we have a factorial ANOVA, 2x2 or any more complex levels, we're looking at interactions and main effects and simple main effects. The first thing we're going to look at is the main effect. We're going to look at the marginal means. In other words, marginal means is just a way to say we're looking at the levels of factor A, ignoring all other factors. And the marginal means of factor B. We're looking at factor B, ignoring all other factors. The interaction is when one factor depends on the level of another. The trends for level 1 of a factor are different from the trends of level 2 or 3 of that factor. That we find there's differences occurring above and beyond the main effects. And when we find an interaction, the first thing that tells us is that's what we really want to talk about. We really want to focus on the interaction in our discussion and even in our results, because that's actually telling us a lot more than the main effects are telling us. And finally, when we have an interaction, we have to go digging deeper. Where are the differences? We have to conduct simple main effect tests. And these are basically simple small ANOVAs being conducted on each level of the independent variable. So simple main effect test to see how each level of factor A was affected by factor B and how each level of factor B was affected by factor A. The final thing we need to talk about is the size of the effect. So when we find significant differences, we also need to get an effect size. Now you can of course ask SPSS to provide these, but I want to talk a little bit about where these are coming from. And there are two types of effect sizes for ANOVA. We've primarily been talking about the partial eta squared, and this is the one that most people use. The partial eta square is basically looking at the unique variance explained by any one predictor divided by that variance plus error. So it's basically telling us the unique variance. What is the unique effect of A? What is the unique effect of B? And what is the unique effect of the interaction? And we're getting these from sums of squares. So we can take that directly from the SPSS table, find those sums of squares, and we could hand calculate this very easily if we wanted to. So in this case, if we did those hand calculations, we'd find that the partial eta, the squared, the actual effect size of the main effect of A is 0.32. The effect size of factor B is 0.28. The interaction in this particular data set is 0.01. So very small effect of interaction, probably not significant. There is also the full eta squared. Full eta squared is actually how much variance is explained of all of the variance. So basically, this isn't just the sums of squares of A divided by A plus error. It's sums of square of A divided by total variance. And these numbers are always going to be somewhat smaller. And they're basically, again, they're telling us something different. If you're really interested in focusing on what is the unique contribution of factor A to all of the variance in the study, then you'd be using full eta squared. And these also relate very much to the effect sizes we talked about in multiple regression. And again, you probably have already kind of recognized that, hopefully, that when we're looking at partial eta squared versus full eta squared, what we're looking at is partial versus semi-partial correlations from multiple regression. So remember, a semi-part or part correlation is the same as full eta squared, and it is the unique contribution of a variable, A, over all of the variance in the outcome. So if we are looking at commitment on years of marriage and we wanted the actual full eta squared, we would be looking at what is the unique contribution of commitment to years of marriage, A, over all of the variance in years of marriage. The partial correlation in multiple regression is partial eta squared, and that asks what is the unique contribution of A over the unexplained variance in years of marriage, A divided by A plus E, unexplained variance. So again, usually we're going to report partial eta squared. We could report full eta squared depending on what your hypotheses are and what you're trying to communicate, but I want to make sure you understand what we're reporting. So partial eta squared is a representation of the unique explanation of that IV on the unexplained variance that isn't explained by any other variables in our actual DV. So as I said, for this lecture, I've been focusing exclusively on the 2x2 factorial ANOVA, the simplest form of the factorial ANOVA. But I also mentioned you're not limited to 2 factors or 2 IVs. You can get as complex as you want. You may use as many factors as your hypotheses require. However, consider interpreting interactions for each J-way interaction. There is a J number of factors. So what that means is that for 4 factors, if we have 4 factors, we have a 4-way interaction, we have 3 3-way interactions, we have 6 2-way interactions, we have 4 main effects, and potentially lots and lots and lots of simple main effects. So just recognize that as we move beyond a 2-factor 2x2 ANOVA, everything that we add, even going to a 2x3 ANOVA, we've now added the need to do post hoc tests if there's a main effect for that factor that has 3 levels. We also have a more complex interaction if we find that interaction for us to figure out what's going on. We now have 2 more simple main effects that we have to run. So again, just recognize that this can get extremely complex as far as thinking your way through it and systematically doing the analysis. However, we're not changing the tools. You're simply using all of the tools we've already talked about. You just may be using them a lot more, and you may have to be really careful in how you think your way through what you're actually finding, especially with interactions. So for example, again, going just one level higher, the 2x3 interaction, we now have simple interaction effects. So 2 or more 2x2 factorial ANOVAs. So one thing that we can look at is if we're actually looking at the interaction between a 2x3 design, So the lines, blue and green, are our factor with 2 levels. That's our first independent variable. Our second independent variable actually has 3 levels. So it's time 1, time 2, and 3. So when we actually look at the interaction, what we're really needing to think about is how does that interaction change over time? So what's happening here is that we find that there is a significant improvement from time 1 to time 2 with the green group, which is the experimental group versus control. However, when we go from time 2 to time 3, we don't find that improvement anymore. In other words, it levels off. And again, from time 2 to time 3, there is still no difference in the control group. So what this shows us is this is actually a pretty good illustration that our experimental group actually initially has a pretty big impact on our DV, our outcome. But once that impact is done, it just maintains, while there is no difference in our control group. So it's not that we can't ask interesting questions with these types of designs, just recognize that even just adding one additional group to one of your IVs makes the analysis a little more complex. We're having to do more. We're now having to add post hoc tests for that 3 levels, and we're having to actually think a little bit more deeply about what those simple main effects are telling us. Now, if we're actually looking by a 2 by 2 by 2 design, so again, we now have just added an additional independent variable. At this point, we've got an example where we've got gender, male or female, we've got treatment, experimental versus control, and we've got time 1 versus time 2. In this case, it's probably better to just start making multiple figures. So what is the difference between males, whether they were in the control group or experimental group from time 1 to time 2? We find very little difference for males. What was the difference between females between time 1 and time 2 is we actually find an improvement. So this would actually be an example of going a little bit more in detail of kind of the example we've been talking about, cognitive behavioral therapy versus psychodynamic theory therapy, but we're now also looking at time 1 versus time 2. Now again, you can kind of get an idea that these are getting a little more complex, a little harder to visualize, a little harder to be able to work through and be able to communicate clearly. And again, these are just very simple additions over the 2 by 2 ANOVA. So my general advice is that beyond a 2 by 3 or 3 by 3 design, beyond 3 independent variables, a 2 by 2 by 2 or a 2 by 2 by 3, you probably want to start really asking yourself, do I really want to do this if I'm going beyond those levels? So a 2 by 2 by 2 by 2 design by itself is a pretty complex design to be looking at the interactions, especially if you find a 4-way interaction. And remember, you're also going to get information on all the 3-way interactions and the 2-way interactions. So you're going to be needing to look at all of this to try to get a good picture. So you really want to make sure that your hypotheses require this level of complexity. So I've kind of joked here that if you go to this level, you should quit and become a goat herder. So seriously, give it up, design simpler experiments, or get it out. I'm not necessarily extremely supporting this viewpoint, but you do want to be very serious and purposeful if you find yourself moving towards such a complex design. It may very well be the design you need to answer your question, and if so, then you need to do it. You need to actually go through the process. Just recognize it is going to be difficult. But a lot of the times, you may be adding complexity that doesn't need to be there. And if you don't need it to answer your hypotheses, it's better to design a simple experiment.